You know, when you look inside pretty much any piece of modern electronics, your phone, a car, even medical equipment, you might wonder how they build such complex stuff. Well, a lot of it boils down to one single incredibly powerful component. Today, we're going to talk about the operational amplifier, or op-amp. It's the true building block of just about everything.
Honestly, the best way to think about an op-amp is to picture it as the ultimate Lego brick for circuit designers. It's a simple, standard piece, but with it you can build an almost endless variety of powerful, complex circuits. It is the one little chip that unlocks a whole world of creativity in electronics.
So, here's what we're going to cover. We'll start with why it's such a fantastic building block. Then, we'll meet the perfect or ideal op-amp to get the basic rules down. After that, we'll look at two of the most common ways to use it, get a peek at some advanced stuff, and then, we'll bring it all back to earth with a necessary reality check.
Okay, so why do we keep coming back to this Lego idea? Well, because that is exactly how op-amps are treated out in the wild. They're what make really sophisticated design accessible to pretty much everyone.
This right here, this is the secret sauce. By treating the op-amp like a simple block with a few easy rules, students, hobbyists, engineers, everyone can just skip the super complex physics happening inside and jump straight to building interesting, useful, non-trivial circuits. It's a huge motivator and it just massively speeds up learning and innovation. It's a total game changer.
All right, to build with these blocks, we've got to know the rules of the game. And the simplest way to do that is to start with a perfect theoretical version, the ideal op-amp.
At its absolute core, this is all an op-amp really does. It looks at its two inputs, measures the tiniest little difference in voltage between them, and then bam, it multiplies that difference by a ridiculously huge number. That number is called the open loop gain. That's the one job it has.
Now, in our perfect world, the ideal op-amp has these perfect traits. Think of them as superpowers. Infinite gain means it can amplify literally anything. Infinite input impedance means it can look at a voltage without drawing any current, so it doesn't mess with the circuit it's measuring. And zero output impedance means it can power any device connected to it without even breaking a sweat. Assuming these perfect rules makes designing circuits incredibly straightforward.
So, how do these perfect rules actually help us build stuff? Well, it turns out that by just adding a couple of resistors, we can make the op-amp do some really cool things. Let's look at the two most fundamental ways to set one of these up.
These are the two workhorses of op-amp design, the inverting and the non-inverting amplifiers. They both amplify a signal, but they do it in slightly different ways, and which one you choose just depends on what you need that circuit to do.
Okay, so in the inverting setup, the output signal is basically a flipped upside-down version of the input. And check this out. This shows the pure magic of the op-amp model. The amplification or gain of your entire circuit isn't some complicated internal number. Nope, it's just the ratio of two resistors that you pick. You want to multiply your signal by 10? Just make one resistor 10 times bigger than the other. It's that simple and predictable.
The non-inverting setup does the same job but keeps the output signal the right way up. And the formula is just as simple. Now, a really cool version of this is the unity gain follower. Here the gain is exactly 1. It doesn't amplify at all. So why use it? Because it acts as a perfect buffer. It's like a bodyguard, isolating one part of a circuit from another so they don't interfere. It plays a super important protective role.
But just amplifying signals, that's really only the beginning. The true power of this little building block starts to shine when you use it for way more complex jobs, even for doing math. For instance, you can build a circuit that only amplifies the difference between two signals. That's absolutely crucial for getting rid of noise in sensitive measurements. And this is where it gets wild. If you swap out the resistors for other parts like capacitors, you can make the op-amp do calculus. Seriously, you can build circuits that integrate or differentiate a signal over time. This is literally how old-school analog computers worked.
So far, we've been living in this perfect, beautiful world of the ideal op-amp. But of course, in the real world, no component is perfect. And this is why that ideal model is so important. Not because it's true, but because it gives us a perfect blueprint to compare against. Good engineering is all about understanding how a real op-amp messes up that blueprint and then figuring out how to deal with it.
So, in the real world, the gain isn't actually infinite, and it starts to struggle at really high frequencies. That's what we call finite bandwidth. Little unwanted DC errors can also sneak in. So engineers spend their time managing these things, like tiny offset voltages, little bias currents, and something called slew rate, which is basically just the top speed for how fast the output can change. Let's just focus on one quick example. Our ideal model said zero current flows into the inputs, right? Well, in a real op-amp, a tiny little bit of current, called bias current, has to flow in to make the internal transistors work. And that tiny current can flow through your resistors and create a small, but sometimes very significant voltage error at the output, totally messing up your precise calculations.
And this is the part I love about engineering. Often these real-world headaches have these beautifully simple, clever solutions. For this bias current problem, it turns out that by adding just one more carefully chosen resistor, you can make the errors created by the two inputs almost perfectly cancel each other out. It's just an elegant, simple fix.
So let's pull all this together. The op-amp is our ultimate electronic Lego brick. We use the ideal model to make designing with it super easy. Its two main moves are the inverting and non-inverting setups, where the gain is set by a couple of resistors. But you always have to remember that real-world limits are what define the boundaries of what you can actually pull off.
The op-amp is just a perfect example of how a good abstraction can be so powerful. It takes something incredibly complicated, a chip with tons of transistors, and boils it down to a simple, predictable block with just a few golden rules. So the real question is, once you know the rules of the game, what will you build with it?